Okay, so this is the first supplement.
Module 2.3, Modeling Using State Space. So consider the following translational system. First, translational systems have defined state variables, which are, wait, I'll write it smaller. State variables, which are x1, which are the outputs. So if there are two outputs, it's going to be x2, x3, x4, and so on. But in this case, it's only one variable, so there, x1 and v, which is the velocity. So if we are to write its standard equations, we identify its equations. We can write it in the S domain, which is going to result into m s squared or s squared m s squared plus, from this, since mass would equal to the s squared, friction is equal to s, and k remains as s, which is the spring constant. So it's going to be c. Oh, actually, the reference we are using here refers to the force generated by this as p, which is the dampening force. So that would be the one I'm going to use. So it's going to be b s plus k, all of which multiplied by x1 of s and with an output of f of s. Now we turn this into its differential equation form by distributing x1 to these values. So it'll become ms squared ms squared x1 of s and so on. We will now combine the s squared with the x1 of s so that we can write it as d squared x1 over dt squared. But instead of writing it this way, I will write it as x double dot. Right. Okay, so continuing forward, this will become mx double dot x1 double dot plus bx1 dot plus k x1 equals f of t. Now with that, let's identify some equations. This will be the general equation, but I will not use it as equation 1 first. I will use this as equation 1. So this output force is x1, and outputs for translational systems are written as z. So I will write it as z. Z is equal to x1, and that's the first equation here. And second equation, we're supposed to get the differential, or we're supposed to get the derivative of the state variables when writing the state equation. So we need to find x1 dot and b dot. But x1 dot is also equal to v, since the derivative of the displacement is equal to velocity, and since x1 is displacement, its derivative would naturally be its velocity, and this will become acceleration. But for now, this is what we are interested in. I'll erase that. Okay, and I will put this equation here to the side. Again, this equation here to the side. Okay, so that would be my second equation. And for the last equation, since I already have the equation for x1 dot, I need the equation for v dot. So v dot is also located here, as we all know, since v dot is equal to the derivative of v, and v is also equal to x1 dot, then naturally v dot would be equal to x double dot, which is here. You can already see in the standard equation that we derived earlier. So by doing so, I can write it as, by putting these two to the right hand side, I can write it as mx1 double dot equals bx1 dot negative bx1 dot minus k x1 plus f of p. Now, to isolate x1 double dot here, we divide everything by m. So this becomes that. This is negative bm, negative km, and f over m, or 1 over m. Okay, so we have to remember this equation. This is the third equation. So I will proceed to the next page. There's no more space. Okay, so this documents page 2. This is trash, and this is also trash. I need to duplicate this. Okay, so open import. So now we have these equations. So we already have the first part anyway, so I'm going to erase some of these. This first part in particular. There we go, and I will be taking these two, putting them up here. I do not know how to scale them though. Yeah, I don't know how to scale them. And this third equation, I'll put it up here. Okay, so we are now going to write the state equation. So the input state equation, we write it as the state variables derivatives, which is x1 dot and b dot. Now the state equation, the input state equation. It's helpful to remember that this is x1 and this is b. These are simply markers. They are not part of the written equation. They only serve as a guide. So the state equation still naturally be multiplied by the state variables, which are again these two, x1 and v. So now for the first equation, for the equation of x1, we know that x1 dot, we know that x1 dot is equal to v. So it doesn't have any input here for x1, and it has 1 as its input for v. Now for v dot, which is this, remember that this is also v dot. Wait, this is also v dot. Yes, okay, that's also v dot. So, and we have a value of x here, and we have a value of v here. This is also v. This is v dot, and this is simply x1. It's written here. So let me just take that out. Okay, continuing. So I continue forward. Okay, so this is again v. So this is negative bm. This value is negative km. This is x1. X1 is located here. I will clarify the marker. X1. There, x1. So this is negative km. And we add here the output, which is f. For the first equation, there is no f. As we can see, we use equation number 2 for this one, and it has no inputs of f, so this is 0. But here we do have an equation of f, which is fm, 1 over m. This is f, and this is 1 over m. There, we just don't write the 1. So this is 1m. So that's for the input equation. And now for the output equation, we write it as z is equal to the marker serves the marker still stands here even if we are now at the output. So the marker still stands, so this part is still x1 and this part is still v. And we multiply the state variables here. Wait, can this be seen? Yes, okay. It's recorded. This is the state variables multiplied here, so, and we add the feed forward equation. So here we focus on this part, and we know that from the first equation, actually, we can look here. We know that z is simply equal to x1, the displacement of x1, And since there is no input for b, this is automatically 0. And x1 would be 1. Now, clearly there isn't any f in this equation, so we're going to write it as 0. So that's the first sample for, or the first supplementary problem for modeling using state space.